Welcome back to Daniel's Extra Chemistry Help Classes. I've seen that many of you have subscribed and given suggestions, and I've just noted those. I want to remind you that a motivated, focused, and sustained hard work is needed for succeeding in any subject like chemistry. Okay, let's think. In the last class, we have discussed classification of matter, base units in the SI system, prefix multipliers, scientific notation for writing numbers, and different temperature scales and their interconversions. And today we will be just going over two most important concepts where students struggle, namely uncertainty in measurements and also dimensional analysis, okay, for problem solving. Now, in the uncertainty of measurements, we have estimated digit in a measurement, number of significant figures in calculation, and also rounding numbers to reflect the correct number of sig figures. Okay, dimensional analysis for problem solving, we have equality and conversion factors, and then we'll be doing a few problems to make everything clear. Okay, so the uncertainty in measurement and also how many significant figures should come in that measurement is a very important thing when we do measurements in the lab. So usually we do this as an activity in the class. I give the students two rulers and then ask them to find the length of a metal bar using the first ruler and the second ruler. So the first ruler is actually graduated as 0, 1, 2, 3 units only, and students will place the metal bar from the 0, one end of the metal bar at the 0, and then they will extend it it to the how far it can go on the ruler, and they find that it actually covers 2, goes beyond 2, but it does not reach the unit 3. So I asked them to just estimate how much part of the unit is that particular point from 2. So students will actually look at that, and most of them will say that is approximately half of the unit. So most of them will say it is a 2.5. But some students are a little critical, and they say that it looks like a little more than 0.5. They say that instead of 2.5, it's better to write 2.6. So basically, the last number or the last digit in the measurement has some type of an uncertainty, and usually that digit is usually called as the estimated digit. Okay, and then I asked the students again to measure the same metal bar using the second ruler. They will place the metal bar again on the second ruler, and here this ruler is a little different. Every unit is again subdivided into small divisions. Each small division is a 0.1 unit. So you can read 0.1, 0.2, 0.3, etc. So they will place the metal bar on the second ruler, and they find that the metal bar comes to, beyond the 0.5, and then a slightly more distance on that. And then I will ask them to again estimate. And many of the students will say, oh, it's approximately half, so they will add one more digit, a 5. So 2.5 is already known or is certain, and then they will add the next digit, which is the estimated digit 5. And some of the students again will have some critical minded, they will say that maybe it's 4, so it should be 2.54, they will say. So again, the last digit is uncertain, the estimated digit is uncertain, while the first two digits are certain. So in any measurement, we have certain digits, and the last digit is always going to have some uncertainty. And when you count the number of significant figures in any measurement, the rule is you count all the certain digits in the measurement and also the one estimated digit, and that together gives you the number of significant figures in the measurement. For example, in this case, the first ruler gives a 2.5, and that has got 2 significant figures. And then the second measurement has 2.55, so it has got 3 significant figures. That's the thing which is coming out of that. Then I'll ask the students, why do you get 2 different significant figures for measuring the same metal bar? Most of the students will say the second ruler is more, sensitive, or it has got more divisions, and you are getting a better, measurement by using the second ruler. So, what does that mean? The points to remember in this case is the number of significant figures depends upon the initial measurement of that particular that quantity, and also the more the number of significant figures in a measurement, more accurate the measurement is. Keep this in your mind when you are dealing with significant figures when we come to. So this is a very important thing in chemistry. Okay, now let's think about somebody measures a measurement, and then you are given the value. How will you know how many sig figures you have to keep? Now there are some certain basic rules for finding the number of sig figures. Okay, now in a measurement that is reported, all non-zero digits are significant. Now we have to be careful about all these things. Keep that surely in your mind, because we don't need any confusion in this case. All non-zero digits in a measurement are significant. For example, if there is a 285 centimeter, then we have 3 significant figures. And if at a 0.25, remember the 0 says that there is no whole number. It's just there to say that there is no whole number part. So the 0.25, there are 2 non-zero digits, and it has got 2 significant figures. Okay, now preceding zeros are not significant. That means the zeros coming before a non-zero digit in a measurement, they are called as preceding zeros. They are usually called as placeholder zeros, and they are not significant at all. Okay, so in this case, we have 0, 0, which are not significant, and then phi 2. So the phi 2 qualifies for your significant figure. So we got 2 sig figures in that particular measurement. Now, zeros between non-zero digits, actually they come while we are measuring, and so they are significant. They come into measurement by just when you are measuring the particular values or particular measurement, so they are significant. So inner zeros, let's call them as inner zeros. Inner zeros are significant. Okay, now zeros at the end of a number are significant provided, this is the case where there is some type of a condition. So we have to be careful in this case. To make it simple, zeros at the end of a number are significant, or let's call them as ending zeros, provided there is a decimal point anywhere in the number. It should be shown on the measurement, the decimal point. For example, if you have a 0.200, now that has got 2 ending zeros, but there is a decimal point clearly shown in the measurement. So this has got 3 significant figures. In addition to the 2, we have 2 zeros which are significant. A 100.0, again the number has a decimal point shown on that. So the ending zeros qualify as significant figures. So total we have 4 significant figures in that particular measurement. While if you think about 100, we have no decimal point shown on the measurement. So those 2 zeros does not qualify, or do not qualify. So we have only 1 significant figure for that measurement. I think this is clear to you. Now, counting number of objects, okay, have infinite number of significant figures. What does that mean? When you count, for example, I count the number of boards actually here. I just say count as 1, 2, 3, 4. That is 4 boards there. There is no 4.1 or a 3.99. That doesn't come there. So there is no uncertainty, and counted numbers are called as exact numbers. And since there is no uncertainty, according to our idea of significant figures, that should have infinite number of significant figures. Keep this in your mind while you are actually dealing with those measurements. Okay. Finally, numbers written in scientific notation. You remember we have two parts. First part actually are the digits, and the second part, the exponential part, is just saying the value of the measurement. So the number of digits coming in the first part, all of them are significant. For example, 4.01 10 to the power of 2, we got 4 significant figures for that measurement. 8.256 10 to the power of negative 3. Again, first part we have 4 significant figures. So it's pretty easy in the case of if you got any difficulty writing a number, always try to write it in the exponential form, which is a better form of representing the significant figures. Okay, now let's think about you measure and then use that measurement in calculation. So when you calculate, if you calculate using a usual calculator, it can give you a number of digits in your answer. But how many significant figures you can keep in the answer? Okay, that depends upon the significant figures in your measurements we are using for multiplication or division or adding, subtraction. So let's think about some simple rules for that. The first thing is, I just given you the basic thing so that you can remember this. Okay, when you do add and subtract, addition and subtraction, we keep the minimum number of decimal places. So the places coming after the decimal, they are called the decimal places. For example, let's take this particular addition. So we got 3 measurements you are adding together. When you are adding together or subtracting numbers, we only look at what? The decimal places. So the first number has 2 decimal places, the second number has 1 decimal place, and the third number has 3 decimal places. So what is the rule? You have to keep the minimum number. That means only 1 decimal place you have to keep in the answer. So when you add them together, you get 31.122. So only 1 decimal place is needed. So the rest you have to cut off. And when you cut off, so you have to round. And we'll be coming to around the rules of rounding very soon. But just remember, the number which is cut off, if 5 or more, you have to add 1 to the last, digit. Or if it is less than 5, you can just leave that as such. So this is the idea. So the answer is going to be 31.1 in this case. Okay. Now, in multiplication and division, just look at this. Keep the minimum number of significant figures. So just remember that. Don't forget this idea. So significant figure is the thing when you multiply or divide. So let's take this particular case. 2.5 you are multiplying with 1.25. It's a multiplication. So the rule is what? The first number has got 2 significant figures. Second has got 3 significant figures. So you have to keep what? The minimum number of significant figures. The answer when you calculate in your calculator comes as 3.125. So you have to count from the left and keep 2 figures, means we count 3 and 1, then you have to cut at at 1. The number which goes out is 2, which is less than 5. So you can just keep 3.1, which is your answer. Okay. Now, what is the rule of rounding? We already have said something about that, but to make it more sure, let's say what is the rule of rounding? So when you round a number to a particular number of significant figures, so add 1 to the last digit in the in the answer if the nearest digit in the part cutoff is 5 or greater, and if the digit cutoff is less than 5, just keep the last digit as such. Okay, so what is the example? So I'll take a typical example. So if you're rounding 124.56 to 4 significant figures, you count from left 1, 2, 3, 4. So you have to cut at 5. So the number which goes out is 6. So the digit which is cut off is 5 or more. You have to add 1. So the 0.5 become 0.6. So the answer is going to be 124.6. This is the idea. But one more thing you have to be careful about. Children always get into wrong results. If you want to round a number, always keep the value of the initial number in your answer. For example, suppose we have a 23,658. You have to round that into 3 significant figures. So you count it from the left. 1, 2, 3. So you have to cut at 6. So the number which goes out is 5 and 8. So you have to add 1. So it will be 237. So in the place of that, can we round it as to 237? That is wrong, because the number was a 23,000 number, and if you just say 237, that doesn't actually match. The value doesn't match. So what's the idea? The number which is cut off, if they are whole number part, then you have to replace them with zeros. So you can say 23700, that actually gives you the values 23,700, or you can keep that in the form of a scientific notation. This is the thing which you have to be careful about when you are rounding numbers. Okay, now let's do a little practice by using this idea. Express the following in the scientific notation, and the best practice is to keep the number of significant figures. Whatever number is given, those significant figures should be coming in your answer. For example, 0.0048. Now think about how many significant figures we have. We have 2 zeros which are preceding, and remember, preceding zeros are never significant. So we have only 4 and 8, 2 significant figures. You have to take the decimal point from here to here. That means you are moving 3 places to the right. So you must have a 4.8 and a 10 to the power of what? -3, which is the answer to that. Let's take the next one. 500.0. Now, this number has 3 ending zeros. And what's the rule? The ending zeros are significant if there is a decimal point shown. Now, this number shows a decimal point. So, those are significant. Those zeros are significant. So, this number has, 4 significant figures. All of them should come in your answer. And you have to move it to the standard form. That means you have to bring the point to 5 point, and you are bringing, 2 places to the left. That means the answer should have a 10 to the power of 2 to balance the value. So it's 5.000. This all has all the significant figures, and the value is, corrected by 10 to the power of 2. Okay, let's come to this number. Now, can you say how many significant figures you have here? You have ending zeros here. And this number does not show a decimal point. So naturally, we have only 3 significant figures that the ending zeros does not qualify according to our rule. So the 1, 2, 6 should come into your answer, but you are changing the assumed decimal point, 3 and 2. That means 5 places to the left. So the answer should be 1.26 times 10 to the power of 5. That should be the answer, which is the correct way of actually representing this in the scientific notation. I think you get the idea now. Now, let's, do this. Round up the following up to 3 significant figures. Okay, we have 2 numbers given. So what's the idea? You just only need what? A correction, up to the 3rd significant figure. So go from the left, count up to the 3rd significant figure, then cut it off and then round. So just go from here. You remember the preceding zero is never significant. So you go count from 4, 5 and 9. That is the 3rd significant figure. When you cut away the 7, you add 1 to the last 9, so it becomes 460. So you can put the answer as 0.0460 or we can just do that in the scientific notation. Second number, 2808. Again, count from the left. 280, that's the third significant figure. You're cutting away the 8. You add 1 to the last number, and remember, there's a whole number part which is cut off, so you have to have what? A 0 at the last place. So that is our idea, remember? So it should be 2810, or we can represent in the scientific notation, which is a better way of representing any number. So the answers are 0.0460 and 2.81 times 10 to the power of 3, which actually gives you the correct value. This is a 2000 number, and this also should be a 2000 number. Okay, now let's do some practice in calculations thing. The question is, how many significant figures should be present in the answer of the following calculation? Okay, now we have multiplication, and then a division. And remember, the rule for multiplication and division are what? Keep the minimum number of significant figures. That's the rule. So just count how many significant figures we have here. The preceding 0 doesn't count. So this has got 4, this has got 5, this has got 3, this has got 4. What's the minimum? Minimum is for 0.112, which has got 3 significant figures, and your answer should have 3 significant figures, whatever be the answer. So, the factor with the least significant figure has 3 significant figures, so the answer should be having only 3 significant figures. Okay, let's take another one. Now, here we have additions. Okay, 3 numbers are added. What is the rule for addition and subtraction? Keep the minimum number of decimal places. Okay, now remember, decimal places means the places comes after the decimal. So this has got 1, 2, 3, 4 decimal places. This has got 4 decimal places. This again has got 4 decimal places. All of them has got 4 decimal places. So the answer should have, according to our rule, 4 decimal places, but they are asking about the number of significant figures. So you have to check whether they add together giving a whole number part. So just if you add them together, what do you get here? You're getting a 0.8204. So fortunately, we don't have any whole number part. So you have to keep all the 4 significant figures, decimal places there, and the number also has got 4 significant figures. That's the answer. So all numbers are 4 decimal places each, and the answer should have 4 decimal places, and also the number has 4 significant figures. That's your answer. Okay. Now we are coming to the second part, dimension analysis. Okay, dimension analysis is a very important, problem solving tool in chemistry and, different sciences. It's pretty simple, but you must get the idea, how this works. For example, if you want to change meters into centimeters, we use the, SI system or metric system, where we know that 1 meter is 100 centimeter. We use this as a conversion factor, and we can actually change by using the conversion factor of the meter to centimeter. This is the basic idea there. So we are going to convert units. One measurement unit is converted to another measurement unit. And sometimes you are going from one system to another. Means what? You're going from a British system to an SI system. You can have a change in the SI system to or other systems also. Okay. Now we need equalities connecting these units, and if the equality is, for example, if the equality is 1 inch is equal to 2.54 centimeter. That equality can be used for making 2 conversion factors. What is that? Now, we can divide the 1 inch with the 2.54 centimeter. That will actually make 1 conversion factor, or the inverse of that, 2.54 centimeter over 1 inch. These 2 are the conversion factors coming from that equality. So every equality can give you 2 conversion factors, and they can be used for converting one unit to another. Now, what's the secret of a conversion factor? Remember, these 2 values are equal. So if you just divide two equal values, the answer is going to be 1. So the first or the second conversion factor, the value is 1, and so if you are multiplying any measurement with a conversion factor, the value doesn't change. The only change is in the unit. So that's the secret of a conversion factor. Okay, let's think about a problem. Now, if you're given a problem, you're going to analyze it, just like a detective analyzes a case file. Look into that, and you have to find out what is given in as a data, and what is wanted. There will be a question there. So for example, in this case, we are having given number is 3.00, and what is wanted is asking about centimeter. And also, an equality is already given. 1 inch is 2.54 centimeter. Fortunately, see, the inch and the centimeter are connected by this conversion factor. I mean, the equality. So, as we have discussed in the last, slide, we have two conversion factors coming out of this. Okay. Now, which of them we will use here? We have to what? We have to cut away the inch, and you have to get the centimeter. The rule is what? Whatever unit you want, you keep on the numerator. So if you use the second conversion factor here, the inch and inch will cancel off. And what you get is going to be centimeter. And remember, this value is converted into, centimeters. Without actually, you're multiplying with the conversion factor means what? There is no change in the actual value. It's only a unit change. And one more thing you have to remember. Conversion factors do not change the sensitivity of the initial measurement. So they do not change the sig figure of the calculation. That means the 2.54 and the 1 inch, which is the conversion factor part, there's nothing to say in the initial measurement, that significant figure. So always remember that idea. The significant figure, you just remember, they are having no effect on the number of significant figures in the answer. So whatever you have in the initial measurement, which is 3 sig figures here, they should appear as the number of sig figures in the answer. So you have to keep 3 sig figures in your answer. So since you are not changing the number of sig figures, a conversion factor is not changing, the significant figures. It's just like a counted number. A counting number, is an exact number. In one way, you can say that a counting number is and a conversion factor are almost the same. We can call them as exact numbers in a way. Okay. Now, suppose we have a multi-step conversion. For example, this question: a hybrid car Prius has a mileage of 52 miles per gallon in the city. How many kilometers can the Prius travel on a 15.0 liter of gasoline? Now, what is the idea? We analyze the problem. So, what are the different parts of doing a problem, multi-step problem like this? You have to find out what is given, the data which is given in the problem. Second thing is you have to identify what is wanted. Always there is will be a question asking you about what you have to find out. That is a wanted thing. And then you have to find a path. Starting from the given to the wanted, you have to find a path of conversions. And if the data which is given in the problem is not enough, you can also look for what? Standard equalities to find conversion factors. So use standard equalities if you need it. Finally what? Finally use all those conversion factors and then come to the what is wanted thing by calculation. So let's take this and analyze it. So we have what? The given thing in here is we have the mileage, which is 52 miles per gallon, which can also work as a conversion factor. Remember, 52 miles per gallon means 52 miles is equivalent to 1 gallon. So that's the idea which is there. So basically I'm going to take the second thing, which 15.0 liter gasoline as the starting point. That will be easier for us to go further. And what is wanted is asking about how many kilometers. That's what you want. So we have to go from the liters to the kilometer. And now you cannot use this because there is no liter over the kilometer in this one. So what is the idea? We remember that the liter is, a volume thing, and the gallon is also a volume thing. And from, if you're looking at a standard values, you can connect the gallon and the liter. How many liters and gallons are connected together? So that is a standard, connection equality. And also, we can have, the miles and the gallon connected together. And when you come to the mile, how will you go to the kilometer? Mile is a distance and the kilometer is a distance. So you can connect them by using a standard value. So we need the standard data. 1 gallon is a 3.78 liters. And 1 mile is 1.609 kilometer. And we can use them by, and then go from the given to the wanted thing. So what you have to do? The path is this. 15.0 liter gallon, which is the starting point. By using the liter gallon equality, we go to the gallon. And once I get to the gallon, from the gallon to mile, we can use the mileage. Because the mileage and the gallon are connected by that mileage thing. Now, and then the miles to kilometer, we use the last, data which you have. Okay, so the data which we have seen, the last slide is here. We have the mileage, which we can use as a conversion factor. And then we have the gallon to liter connection, mile to kilometer connection. And also we start from the 15.0 liters. So we are going from 15.0 liters of gas to gallon. And then we're using 1 gallon over 3.78 liter. Why? Because we want the gallon. So whatever you want, always keep at the top. Okay, then the gallon to mile, we're using the mile gallon connection. The mile to gallon connection comes in the mileage, and in there you have to keep the 50 mile over gallon, so that the gallon can cancel off and you get the mile. So we need the mile from that. And again, mile to kilometer, since we want the kilometer, you keep the kilometer. So the connection, the equality, 1 mile equal 1.609 kilometer. You can use as 1.609 kilometer over 1 mile, and then you just multiply, starting with the given thing with the conversion factor. So it goes as 15.0 liter, and then the first conversion factor which converts the liter into gallon, times the second conversion factor which converts the gallon into mile, and last conversion factor which actually converts the miles to kilometer, and you're going to get the kilometer. Now you can calculate throughout. Don't stop at any stage. Throughout using a calculator. And then how many sig figures you have to keep? We already know that the conversion factors are not having any effect on the conversion, the number of significant figures. Whatever you have as the initial, sig figures, which is 3 sig figures for the initial measurement, that should come into the last, your answer. So we are going to cut at the third significant figure, and you are, in this case, you are getting 332 kilometer from the calculation. I think you got the idea. It's just a basic idea of analyzing the problem and then coming to the correct, conversion factors to go from the given to the wanted. Okay, now let's do a few problems, where you are just taking all the ideas which you already discussed up to this point. So let's take this problem. Express the quantity 33.1 times 10 to the power negative 4 meter in millimeters. So this is a case of the prefix multiplier thing. So what's the idea? I'm going to use the 10 to the power negative 4. I'm just going to separate it into 10 to the power negative 1 and 10 to the power negative 3. Why? Because I need the milli, and remember, according to our prefix multiplier idea, the milli is 10 to the power negative 3. So I just separated that. And whatever comes here, 10 to the power negative 1, I'm going to combine with the 33.1, which gives you 3.31. And instead of the 10 to the power negative 3 number, I use the, the letter in the prefix multiplier system, which is the milli. So it's a 3.31 millimeter. Okay, let's go to the next one. Convert 23.2 degrees Celsius into the temperature in the SI system. So this is just remembering the base units in the SI system. And remember, I already told you about two important things in the base unit. One is the mass or unit, which is kilogram, and the temperature unit is Kelvin. So the unit in the SI system is Kelvin, and we are very happy because here Celsius to Kelvin conversion is pretty easy. The Kelvin is always 273 degrees more than the Celsius, so just add the 273 to that. So 23.2 added to 273 gives you the answer, which is 296.2 Kelvin. Okay. Now, find the number of significant figures in this particular measurement. Okay. Now that has all the things which you already studied, and this has got a preceding zero, an inner zero, and ending zero. So those zeros are the ones we already know. So we have no problem here. We always know a preceding zero is not significant. An inner zero is always significant. We only have problem with what? The ending zero. And what's the rule? If the number shows a decimal point clearly in that measurement, the ending zero is significant. That means all those digits except the preceding zero are significant. So if you count, you get 6 numbers there. So that means it has got six significant figures in that measurement. Okay, let's go to the next one. Calculate with the correct number of significant figures. Okay, look at that. We have a 7.01 minus 6.50 in parentheses divided by 2.005. Now, this calculation has got two types of calculations according to our rule. Remember, the first part is a minusing, which has got a different, way of calculating the, 6 figures. And the second part is whatever you get out of the minusing, you have to divide with a 2.005, and then multiplication division has got a different rule. So here what you have to do? You have to always go with the hierarchy of calculation. I think you have different mnemonics for actually doing the hierarchy of calculations. One of the hierarchy of calculation, students usually say that please excuse my dear Aunt Sally. Means what? Parenthesis first. Then comes exponentiation. Okay, and then please excuse my dear. That is multiplication and division. They got equal priority. And finally, Aunt Sally. That is addition and subtraction, which is the last thing, which is having equal priority rule. So this is the thing. So the parenthesis should come first according to our hierarchy. So you have to minus this value first and find out the correct 6 figures from there, and then that number should be divided with 2.005. By using our rule, we know that for division we have to have the minimum number of 6 figures. So what we do? We minus 7.01, 6.50. What is the rule? Keep the minimum number of decimal places. So this has got 2 decimal places, this has got 2 decimal places, and you calculate, you get 0.51, so you have to keep those 2 decimal places there. So that's your numerator. Now divide that with the 2.005. That means here this is a division. And what's the rule? Keep the minimum number of significant figures. So the first measurement has got, or the value you got is having 2 6 figures, and the last one has got, divided by that number has got 4 significant figures. How many you have to keep? You can only keep 2 significant figures according to your rule. And if you do this in your calculator, the calculator is going to give you a 2, 5, 4, 3, 6, 4. It gives a number of digits. You cannot keep all of them. You can only keep what? According to our rule, keep only 2. That means go from the left, go to the second, significant figure, cut there. Since the number goes out is 4, you have to keep only the 0.25. So that's going to be your correct answer. I think you got the idea how to calculate such things. Okay. Finally, let's say you got a problem here. Find the volume of 17.8 gram of an aluminum block. with a density of 2.7 grams per centimeter cube. Okay, now what is the idea? You have to analyze it, find what is given, what is wanted, find out a conversion factor, and then do the calculation. It's not a multi-step thing because, the given thing is 70.8 gram. What is wanted is centimeter cube, and the gram and the centimeter cube are directly connected by the density. So we can easily use that. That is actually an equality. See, 27 grams is equivalent to 1 centimeter cube. That's the idea when you say 2.7 gram, and the centimeter cube. That can be used as, that equality can be used to get two conversion factors. And so if you start from your value 70.8 gram, what should be your conversion factor? We need centimeter cube, so you have to keep the centimeter cube on the top and the gram should come down. So this should translate into 1 centimeter cube on the top, 2.7 gram on the bottom, just like that. And then what? Gram and gram will cancel. What you're going to get? What? Centimeter cube. Your answer, you actually got the answer. So just calculate it. And how many sig figures you have to keep? Only look at the first, measurement, which has got 3 sig figures, and your answer should have 3 sig figures. Okay. Now, we have discussed the most important things today. Just keep your, those things in your mind, and just respond. If you can actually subscribe to this so that I can actually get to you very soon whenever actually I am uploading more videos, and send me your suggestions, questions, and even you can give a thumbs up, and I can give you a better sense. Thank you.